Welcome to the Mahatma Gandhi Institute of Technical Education and Research Center. In 2004, a national level institute MGITER has been started in the field of engineering and technology as per guidelines of All India Council for Technical Education AICTE New Delhi. MGITER is approved by AICTE New Delhi, Gujarat State and affiliated to Gujarat Technological University Ahmedabad, which is also known as GTU. Our goal is to be an institute of generative ideas so that we remain relevant to our society. The MGITER has always been an organization on move with continuous effort on improving its processes and to maintain its relevance to the Indian science scenario, with adding new programs in its programmatic portfolio. We strongly believe in overall development of students, so for that we provide them a different platform like state level tech fest, project fair, different sports activity, which helps students to teach teamwork and problem solving skills to get physical health benefits, boost self esteem, and reduce pressure and stress for prove their skills in distinct area. Welcome to the virtual class of design of AC machine. Myself, Professor Gaurang Patel. Today we are going to discuss the concept of specific magnetic and electric loading, output equation of three-phase induction motor, choice of specific magnetic loading, and choice of electric loading. We will discuss this concept one by one. First, we will discuss concept of specific magnetic and electric loading. Okay, so here we can see that in concept of specific magnetic loading, what is the definition of it? The average flux density over the air gap of a machine is known as specific magnetic loading. Okay, what it says, the average flux density over the air gap of machine is known as specific magnetic loading. Average flux density, that is denoted by B average. We will see first of all those things, then I will explain you one by one those things. So just concentrate over here on this equation. B average is equal to total flux in air gap divided by the length of air gap. Okay, so we can write down those equations. So here we write down, that is average flux density, that what we consider average flux density, that is BAV, denoted as BAV, is equal to total flux total flux in air gap divided by length of air gap. Divided by length of air gap. Okay, and it is also, you can write down average flux density is equal to 5p by pi dl. Okay, so here phi, that is stands for flux, and p, that is stands for number of poles. So this phi, that is stands for flux, and this p, that is stands for number of pole. So total flux in air gap, the upper section, that is total flux in air gap, that is equal to 5 multiplied by the number of poles, and the below section, that is length of air gap. This is very important term, length of air gap, which is denoted as pi dl. This I am talking about this term, length of air gap, where d is, we known d is equal to diameter of stator bore and L is equal to length of stator. Okay, we will see it one by one. What is the d diameter of stator bore and what is the length of stator, because if we don't know what is the diameter of the stator and what is the length of the stator, visually we cannot understood those things. So I will show you what is the D and what is the L. Okay, so when you consider L, that is the length of stator, you have to consider this portion, the length of the stator. This whole portion is known as the length of the stator. And when you're talking about the D, diameter of stator bore, so that is the portion diameter of the stator bore. So once you understand visually what is D and L, that it is very easy to understand the concept of the specific magnetic loading. Okay, so once again I would like to say you that is the average flux density BAV is equal to total flux in air gap divided by the length of air gap, which is known as 5p by pi d L. Okay, so if you remember the concept of three-phase induction motor or principle of the three-phase induction motor, we understood that the flux density is going to play a vital role in working of any induction motor. Okay, because this flux links with the secondary conductors, that is rotor conductors. So EMF is induced in that secondary part. Then rotor conductors behave as a current carrying conductor. Those are placed in the magnetic field. That's why it will experience the force and motor will get rotating. This is the basic principle of three-phase induction motor. Keep in mind, please. Okay, now further when we talking about the average flux density and particularly this term, that is the length of air gap. So length of air gap, if you would like to understood the length of air gap, that means what we see in the figure, we know that is the gap between the stator and rotor. Okay, I will just draw those part so you can understand it better. The length of air gap, if you consider the equation, that is average flux density into 5p by pi dl, where this part pi dl, that is the length of air gap. So what is length of air gap? If we draw a circle, if you consider this outer part, that is a stator, and the inner part, that is the rotor. Okay, so when you consider this part as a stator and this inner part as a rotor, so there is, you can see there is a gap in between this. This is known as the air gap, what we are talking about, air gap. And when you measure the length of air gap particularly, so that you have to consider the total length. This will be the total length. If I cut this part from here to here, and if I will measure this length in between this, okay, so this is, I can consider it is as a length of air gap, and which is denoted as pi dl, where d, that is equal to diameter of stator bore, that I just show you in the picture, and L, that stands for length of stator. Okay, why I mainly focus on this part? Because whenever you calculate the example, first step it is, that is, you have to calculate the average flux density of the machine. So at that time you have to keep in mind what is the average flux density and what is the total flux in air gap and what is the length of air gap. So you can easily understand, that is, the average flux density is equal to phi p by pi dl. Now further we okay, so now we have the equation of average flux density, that is total flux in air gap phi p divided by length of air gap pi dl. Further we reduce this equation, that is equal to phi tau by l. This term is known as, this is the known as tau, and tau is equal to pole pitch. Okay, tau is equal to pole pitch. And what is pole pitch? I hope we everybody know about the pole pitch. Pole pitch, that is the distance between the two poles. Okay, if we consider this is your stator, if we have the 4-pole motor, these are the 4 poles, so we can consider this distance this is pole 1 and this is pole 2, if we consider, for example, for our understanding. So distance between these two pole is considered as a pole pitch, and it is given by pi d by p. So if I put this term pi d by in place of this pi d by p, my equation of average flux density is reduced to phi tau by l. Okay, I hope you understand this. Reducing of B average is equal to phi t by l. Okay, so this is the equations for average flux density, that is total flux in air gap divided by length of air gap, which is phi p by pi dl, which is further reduced to average flux density is equal to phi tau by l. Here I will also write it down, each and every terms which included in this equation. Okay, so first we consider tau, that is equal to pole pitch, which is considered as pi d by p. The next phi, that is flux per pole in Weber. P is equal to, as we all know, that is number of poles. D, that stands for diameter of stator bore. Diameter of stator bore. And L is equal to length of stator. So these all are the terms which we are going to use of concept of specific magnetic loading. And generally we will use the range of B average. What is the range of average flux density? Is generally we kept in, it is in between 0.3 to 0.6 Weber per meter square. Okay, for normal design, and from 0.6 2.65 Weber per meter square for special purpose design. So from this explanation, I hope you easily understood what is the concept of specific magnetic loading. Then we will further move to the concept of specific electric loading. Okay, so these are the terms which I already discussed to you, concept of specific magnetic loading, and now we will move towards the concept of electric loading. Okay, so here that is the concept of specific electric loading, which is also known as the, you can see over here, consider as AC, that is nothing but the ampere conductor. So definition of specific electric loading is, just a moment. Okay, the definition of concept of specific electric loading is the number of stator ampere conductors per meter of stator periphery at the air gap, okay, is known as specific electric loading. So the number of stator ampere conductor, this is the total stator conductors divided by stator periphery air gap, which is known as the specific electric loading. We just try to understood those concept of specific electric loading in notes. So specific electric loading, that is given as total stator conductors, total stator conductors divided by stator periphery at air gap, divided by stator periphery at air gap. So total stator conductors, that is nothing but that is the Z, which is known as total stator conductor. Okay, and over here the definition says that it is the ampere conductors, so it is related with the current which is passing through this conductor. So this is the IZ, which stands for current which is passing through this conductor, which is passing through the Z, okay, divided by the stator periphery at air gap. Stator periphery, that means the total area which is covered by the stator periphery, which is known as the pi d. D we all know, that is the D stands for the diameter, okay, diameter of the, we can say diameter of the stator bore as well. So our equation, excuse me, our equation for AC or ampere conductor is become IZ into Z divided by pi d, which is also you can say that ampere conductor divided by pi d, that which is meter, okay, where I already said to you that at IZ, that is the current through stator conductors. IZ stands for the current through stator conductor. Z is equal to total number of conductor, total number of conductors. P we all know that is number of poles. D stands for diameter of stator bore, diameter of stator bore, and L, that is length of stator. Okay, so over here the range of AC, we consider range of AC, that is, I just write it down over here, the range of ampere conductor is 10,000 to 17,500 up to 10 kilowatt. Okay, then 20,000 to 30,000 up to 100 kilowatt, and 30,000 to 45,000 greater than 100 kilowatt. So these are the ranges we can choose for the ampere conductor when in example there is a range is given or there is a capacity of motor is given. Suppose there is a 25 kilowatt motor is given to us, so we can choose the range between for the 25 kilowatt, that is 20,000 to the 30,000. Okay, for the range of ampere conductor. Okay, so I hope you understood the concept of specific electric loading, that is specific electric loading, it's also over here. The definition is the number of stator ampere conductors per meter of stator periphery at the air gap, and it is given by total stator conductor divided by the stator periphery at the air gap, and AC is equal to Iz into Z by pi d, where Iz stands for current through stator conductor, Z is equal to total number of conductors. Those all terms I already explained to you in this note. Okay, in this part of video we just keep this in limit up to this concept of specific electric loading. The another part I will explain you the output equation of three-phase induction motor as well as the factor affecting the choice of concept of specific electric loading and specific magnetic loading. Okay, so this is the question asked in GTU related the choice of specific electric loading and specific magnetic loading. First question, that is explain the factors that the choice of specific magnetic loading which was asked in summer 2018 and winter 2017 and 16. Later two questions I explained to you in my next video. Okay, thank you very much.